Good evening, students. Welcome to week 6 problem solving session on analog electronic circuits course. Before starting, I would like to confirm whether I am audible clearly. And if somebody just
Yes, ma'am.
okay. So, yeah, as I mentioned earlier, here we are facing heavy rainfalls. So, because of which there might be a possibility that my Wi-Fi connection might be disrupted. So, the moment you feel like something is stuck, you are not able to listen to me, please raise your hands or like interrupt me in any way possible, like unmute yourself or you can uh, type a message, whatever you feel like, so that you don't miss upon what we are talking, right? So, with this, let's begin today's session. In today's session, as promised last week, I told you about we'll be discussing gate control. Okay. So, when we talk about MOSFETs, you all might be familiar with like shrinking of MOSFETs, right? Reduction in MOSFET size. So, what is the major reason? Why do we need reduction in size? So, it somewhere leads to gate control because we want higher gate control in the MOSFET. So, that means I want maximum control in my MOSFET based on gate. So, what generally happens when there is a MOSFET? Okay, so in MOSFET, when you start shrinking the MOSFET dimensions, so basically you start shrinking the gate length to improve the device performance. That is to uh, like enhance the current behaviors, and to get better performance from your device. This drain starts creating problems. So this gate, when it comes very close to source, it hinders the control of gate. So that's why we see new devices every now and then, right? We started with planar MOSFET, then came FinFETs, then gate all around FETs. Now we are moving to 2D devices. So the major constraint that we talk about is we want gate control. Yes, please, if you have something, just unmute yourself and ask. Whenever you feel like, you can simply unmute yourself and ask. So, yeah, so as I mentioned, gate control is very important, and we want to have maximum gate control as possible for our devices for better operation, so that there is no leakage. Basically, when drain starts hindering, it leads to leakage. My voice is not audible. What about others?
It's audible.
Okay, so maybe you can check your settings once if I'm not audible. Yeah, so as I mentioned, the gate control is very important. So today we'll be talking about, okay, what is gate control basically, right? So gate control means here we have charge, right? So how much, if I talk about gate control, how my surface charges, this Q, changes with gate voltage. This provides me gate control. So basically, the idea is how my surface charges, which are there, the interface charges, at the gate interface are interacting with the gate voltage, like how sensitive these charges are to my gate voltage. That basically tells us about gate control. If the sensitivity is very high, that means the gate control is very good. If the sensitivity is very poor, then that means the gate control is poor. Now, talking from a formula point of view, so it's basically VB, like, uh, so it's V surface, or yeah, so let's say V surface upon VG. So that this is gate control, okay? So how my potential in the surface is changing with my gate voltage gives me gate control. Now, talking from formula point of view, this is also denoted by M. Talking from a formula point of view, so let's do a small derivation to understand this. Okay, so let's say my source and drain both are grounded. I have a voltage VB here, and this is VG. So looking from this cross section, it appears as a MOS capacitor, right? Between VG and VD. So if I simplify this, I can draw it like there is VG, then there is a oxide capacitor, then there will be another capacitor which will be caused because of the depletion that will be formed here, this depletion region. This depletion region will lead to CD, and then we have VD. So between COX and CD, we have V surface, right? So V surface is here, correct? So this is the simplest way you can represent this particular cross section, right? So in this, we know that C is dq upon dV, and Cox is, we already know oxide capacitance, it is epsilon ox upon Pox. This is per unit area, okay? So we are talking about per unit area capacitance. We know that conductance is I by V. The change in current, the change in voltage gives us conductance. So let's say I want to find GND. GND basically means it's a conduction because of body voltage. So here it will be ID upon VB, right? Change in ID with body voltage VB. So multiplying and dividing it with VG, what we find is GND is this ID upon VG into VG upon VB. So this ID upon VG is GM into VG upon VB. Now we know that there is another potential, that is V surface, present between VG and VB. So let's introduce that as well. So this is GM into VG upon VB into V surface upon V surface. So this will be Gm into Vg upon V surface into V surface upon Vb. Okay. So first, let's find out Vg upon V surface. When we find out Vg upon V surface, so we'll find it out like Vg Cox Cd, and let's say the body voltage is grounded. Okay, so this is grounded, this is V surface. So now if I have to write this V surface. So it is simply, it will become V surface as 1 upon CD upon 1 upon CD plus 1 upon Cox into Vg. Correct? Simple voltage division rule across the capacitance. So if we simplify this, this becomes CdCx by CD into Cx plus CD. The CD cancels. This is Vg. So this becomes Cox by Cox plus CD. So as I mentioned earlier, V surface upon Vg is Cox upon Cox plus CD, and this is what is gate control, correct? So here, if I say that, so if I want my gate control to be best, that means my gate control should come out to be 1. But as you can observe from here, this is not possible, right? Cox upon Cox plus CD would be always greater than Cox. So that means it comes out to be less than 1. So the closer this value, this gate control is to 1, the better your device is. Talking from leakage point of view, okay? So there won't be any leakage and everything. So now to further simplify, let's say if I write it like, so this is your M as well. So Vg upon V surface upon Vg is M, which is your gate control. But in this formula, what we wanted was Vg upon V surface. So Vg upon V surface becomes 1 by M, correct? So this is first part. Now second part in this formula, what we wanted was this V surface by Vb, right? So for V surface by Vb, in this particular scenario, what we will do, again we'll use the same setup. But now here there will be Vb, here you have V surface. At this time, we'll put this Vg point to come. And now again, if we analyze our V surface, it comes out to be 1 upon Cox, 1 upon Cox plus 1 by Cd into, into Vb, right? So here the expression was V surface upon Vb only. So we will have V surface upon Vb as to simplify Cox Cd upon Cox plus Cd. These two cancel. So V surface upon Vd turns out to be Cd upon Cox plus Cd. So now we have these two. So let's substitute into GMB. So GMB becomes GM into Vg upon V surface, Vg upon V surface into V surface upon Vp. So that is Gm into 1 by n. 1 by n being Cox plus Cd upon Cd into Cd upon Cox and Cd upon Cox plus Cd. So GMB is GM times CD upon COX. Okay, so this is CD upon COX GM. Now we know COX upon CD plus COX is M. So 1 by M is CD plus COX by COX, which is CD by COX plus 1. So I can write CD upon COX as 1 by M minus 1. Correct? So I can write CD by COX as 1 by M minus 1. So my GMB becomes GM 1 by M minus 1. So this basically shows you the relation between the like normal conductance, which is gate dependent conductance GM, and the body dependent conductance GMB. So the relation is, now if I write the relation between different conductances that we have, so GM, this is because of gate voltage, okay? So this is larger than GMB, which is body, and these two are much larger than the GDS. This comes because of the like output resistance, right? So this is the gate drain side. This is because of drain. This appears because of the drain. This appears because of body, and this appears because of gate. So from here you can clearly observe that when in a situation, if you face that GM and GMB are present, so GMB is not very small, so you have to consider GMB, but you can neglect GDS. So this is to give a relative idea that okay, how the conductances are present in the device. So the GM, that is because of gate, is the largest conductance available. Then you will have body conductance, which is GMB. It is in comparable range. As you can see, it is GM times 1 upon M minus 1, right? So it is some orders less than your GM. And then GDS is very small. So this is this expression means this relation you can keep in mind. And other than that, the important factor is this gate control factor. So you need to keep in mind. So basically, you need to understand this. Okay, what is gate control? Because when you talk about new technologies, the major constraint that we are worried about is gate control. Other than performance, gate control is one, so that we can get better on-off characteristics. Okay, right. So now with this, maybe let's move into the problems for today. So today's first problem is based on this mirror kind of circuit. So where, see here, you see you have first of all, this is a multi-stage amplifier. So when you have, so when, okay. So there are different kinds of amplifiers, as I mentioned, right? So in multi-stage amplifiers also, there are two types of amplifiers. One are cascade and another are cascade. Okay, so when I say cascade, what I mean is, uh, let's say this is PMOS, this is NMOS. So the output of this is given to the next stage. Okay, so this is my cascade VDD. So this is cascade amplifier. But now when you have this type of scenario, when you have output here, so let's say you have input here, this is output. So in this case, You give input over here and you take output from here. So this particular case is known as cascode. In both the cases, you will get amplification, but there are advantages and disadvantages accompanied with both of these. So we will discuss this in the coming sessions. But for now, just understand that these are multi-stage amplifiers. So the moment you see more number of transistors either stacked one above another, that is also a multi-stage amplifier, or you see multiple in parallel, then also it is a multi-stage amplifier. Okay. So in this particular figure, if you observe very carefully, so this is like talking from one side only, half side. If you observe, so you have a cascode configuration, right? And if we see very carefully, the gate and drain of these transistors have been shorted, right? So when gate and drain of transistors are shorted, so what happens is all these transistors are in saturated. All these transistors are saturated. Now, your gate of the two transistors have been connected. So these gates are connected, your gate and drain are shorted. So this makes sure that if, let's say, in this particular branch ID current is flowing, this other branch will also carry current ID, given that their uh, like sizing parameters are same. So here it is already clear that all the transistors are in saturation. So we know that ID is N Cox W by L VGS minus VTH whole square, right? So in all these transistors, when gates are connected and there is this mirror configuration, like basically when this shorting is there between gate and drain, then that means the other transistor has already moved into saturation because of this configuration. And if their width and length are same, like WP and WP of both the transistors are same. Similarly, lengths of both the transistors are same, then the same current will flow through the other transistor also. This is known as mirroring configuration or mirror circuits. But if you change this parameters of W by L, then things will change as we will look ahead in this particular session itself. So starting with this particular problem. So in this problem, you can see that there are mirror circuits. So one thing to keep in mind always is when you see transistors stacked in series, a single current will flow through the transistor. Okay. When a single current is flowing through the transistor, depending on that, how your things change, that's how the final outcome will appear. So it's a rule of thumb that when the transistors are connected in series, all the transistors will carry same current. Okay. So yeah. So starting with this problem, here we have 2.5 volts. So in this particular problem, it says that R is 3.79. R is 3.79 kilo ohm. WP is designed such that WP is WP is designed such that it is 4 times WM. So WP equal to 4 times WM. And muon CX by 2 is 3.15 meters per volt. And for p-channel AP CX is 0.7 meters per volt. VD of the transistor is zero point 0.3 for both the transistors, and assuming that L is 1 micrometer, L has been fixed. So now, what should be the width WN? So you have to find WN such that I through the devices is 153 microamperes. And here ignore the body effect. So that means body and source are shorted. So here we need to find the value of Wn such that your current flowing through the devices is 153 microampere. So see, current through N-type MOSFET will be mu1 Cox Wn by 2L VGS minus VT whole square. IDP will be mu1 Cox WP by 2L VSG minus VT whole square. Correct? Now here, first of all, we know that the current the current through this is I is 153 microamperes. So if we see this 2.5 ka drop, it is dropped across. This is source drain. So VSD1 plus VSD2 plus I into R plus VDS3 plus VDS4. Correct. Now, if we observe carefully, the VDS and VGS are equal since gate and drain are shorted. So this can be replaced with the VSG1 plus VSG2 plus I into R plus VSG3 plus VSG4. Right? Now, so first of all, let's compute mu and Cox, this part, mu and Cox Wn by 2L. So when we compute mu and Cox Wn by 2L, it will turn out to be, so this is 4 times, right? So WP, so it will be 0.788 into 4 times Wm by L, and here it is 3.15 Wn by L, and then VSG minus VTH square, and there's VGS minus VTH square. So if you calculate 0.788 into 4, what is the value that you get? 0.788 times 4. It's the same 3.15, right? So this comes out to be 3.15 Wn by L VSG minus VTH square. So with this, we can clearly understand that first of all, same current is flowing through IDN, and so IDN and IDP, these two are equal. Now, this 3.15, 3.15, if both are equal, VTH for both the transistors is equal. That means VSG equal to VGS, correct? VSG is also equal to VGS. So from that, I can write it as 4 times VGS plus I into R. Now I know the value of I into R, right? So I can substitute it over here. 2.54 PGS plus I is 153 microamps into R is 3.79 kiloohms. So then by solving this, VGS turns out to be how much? What is the value of VGS that we are getting? Okay, so when you solve this, the value of VGS that we'll get is 0.48 volts. Okay. Now, when we got 0.48 volts as our VGS, we know VGS is 0.48 volts. Iodine is 3.15 into Wn by L is already given to be 1 micrometer into 0.48 minus zero point 0.3 square. So from here, and ID is known to be 153 micro amperes. So by solving this, W1 will become 153 microamps into 1 micrometer by 3.15 millisieverts per volt. And by 0.18 square. So by solving all of this, W1 turns out to be 1499 nanometers, or if we report it in micrometers, it will be 1.499 micrometers. Is this clear? How we solved this problem? How we approached this problem? Is this clear to everyone? Any doubts in this?
How did it VGS is equal to VSD, the overall?
VG is equal to VSD is coming from this. So here, if you observe, your gate and drain are shorted, right, for all the transistors. So when gate and drain are shorted, that means VG equal to VD, right?
Yes.
So from there, we said that, okay, we replaced VSD with VSC, and then
Uh,
we approached this.
in cases where the PMOS or any of the NMOS will have a
Yeah.
different W which are in
Huh.
series,
Hmm.
then the scenario would be different, right? In that case, I mean, because
See,
VSG,
one thing is for sure that your all the transistors will carry same current. So
yes,
let's say your W is changing. For one PMOS, it is something. For another PMOS, it is something. So depending on that, your values will also change. So basically, let's say your process is same. So mu and Cox will come out to be same. W and L are different for the transistor. Then how your current will remain same. So it will either change because of your VTH, or it will be regulated by the VTH difference or by the gate VGS difference, but current will always remain same in series. So that is the key that we have to keep in mind. Key point: the current will always remain same in the series. With that starting point, we should start solving these kind of problems.
right. Okay. Yes, I
Yeah.
mean, so in that case, like let's say if VTH is also same, so VSG or VGS would be
Yes. Yes.
deformed.
So it will
Oh,
depend, right? So it will
oh,
completely depend on the problem. Like if they say, okay, VTH of all the transistors are same, but W's are different, then and process being same, so mu and Cox will remain same, W is different, and VTH is same. So then VSG is the only point. But Yeah, so it completely depends on how the question is formed, right?
Right. Yeah. Thank
Okay, so hope this is clear. Any other doubts? So could you understand how we approach the problem? Like whenever you see things in series, simply apply, simply you have to first assume that current is constant, like same current is flowing through all the transistors. And from there, if you write the current equations of each transistor and equate them to one another, you can solve these type of problems very easily. Okay. Now, moving on to the next problem. Uh, So in the similar fashion, now it is given that okay, this particular transistor earlier we didn't consider the effect of lambda, right? Uh, so lambda was not part of the problem, but now it is said that okay, assume a lambda of uh, zero point 0.1 volt inverse for both the transistors. So this lambda has to be inserted for both the transistors. And what is the small signal gain of the circuit? So if we want to find this, so this is again, this is a CS configuration, right? So CS configuration, for CS configuration, the gain is GM into Z out. This is output. So across this, if I can find the Z, then I'll get the value. So that means it will be like this because of p transistors, like these two transistors in series, we will get an resistance ZT. Because of these two transistors, like PMOS, NPOS transistors, we'll get the resistance as Zn. And then if we find the parallel combination of these two, then it will give us Z out. So when you analyze them, you will find that Zn turns out to be 2GDN plus GMN upon GDN square. So when we solve these two transistors, no, like how these transistors are connected, see this is gate, source, drain. This is source, gate, drain. So one transistor is connected to the source, like the source of one transistor is connected to the drain of other transistor. So when you solve this particular transistor combination, no, you can use a small signal model, and when you solve that, you find this value for that, uh, like when two transistors are connected this way. So you can keep this in mind. This is very simple to remember, and it can be used easily. So simply in the similar fashion, we will have for GDP is 2 GDP GNP upon GDP square. Right? So this is how your Zn and Zp will look like. Now to find Z, now to find Z out, it should be Zn parallel to Zp. Now, as we mentioned earlier, GM is much greater than GDS, correct? So when your GD and GM are in like addition, you can simply neglect that term and it will become GMN upon GDN square, and this will be equivalent to GMP upon GDP square, just to simplify it. Okay. So now the okay, so Zn is equal to Zp, and here the gain will become like this is GDP square by 20 plus GTN square by GMN. This turns out to be Z dot. Also, gain has another formula for this type of circuits, that is minus GM, GM R naught plus 2 R naught by 2. By using this formula, considering that GMN is equal to GMP, well, there is no need to consider. We already found out, right? VGS were same for both the transistors, and everything was same since same current was flowing. So GMN and GP will also be same. And similarly, R naught M is equal to R naught P. So by solving that, by substituting this here, we'll get again the same formula, like gain formula, and from there the value of gain turns out to be minus 6232.0445 volt. So this is like another approach. So this is Z of will be 2 GTN squared del GMP into GM. So it becomes twice of GDN squared by this formula, GM into Z out. By using GM into Z out, the simplified formula turns out to be 2 GDN squared as gain. But if you go by this actual formula, then it gives you this value. But again, it's more or less like similar, just slight difference will be there. So this particular formula is from lecture. So if you have gone through the lectures properly, so you might have come across this formula in the lectures. And this is like the general formula of gain, that is GM into Z. Okay.
Uh, so in this, the gain formula GM into zero, which GM are we going to consider? I mean, of which transistor?
So here in our case, GM comes out to be same, right? Because the same current was flowing and the factors were also coming out to be equal. So
Uh,
that's why GMN equal to GMP. And in most of the cases, since the same current is flowing through the devices and considering like VGS is almost same, so there you will find this kind of scenario only. The like conductance of both N and PMOS are.
uh,
Otherwise, if they are different, so then it will be. So this formula is like simplified versions, right? So this is for considering that GMs are equal, R naughts are equal, GDs are equal. By that you come to these simplified formulas. If in case there are like there is some question where you find that GMs and GDs are completely different for NMOS and PMOS, then you have to solve them systematically. So then it won't come to this simplified formula.
so in this case, in that case, like when they're different, we have to take basically the small signal model
Yeah,
of
yeah.
all the
Small
transistors and then
signal
solve
model
it.
of the transistors and then solve. That is the best way. So you won't make any mistakes and you'll reach the correct results. But
Oh,
for the problem's sake, that never happens. It is always the case because your currents remain constant. So generally, your GMN and GMP also remains constant. And so you always boil down to this simplified formula only. But in case if you feel that okay, in certain question it might have made like it might have been made tricky, and because of which you find that GMs and GDs are different. So simply the best way is draw the small signal model, properly draw the small signal model and solve that small signal model. Okay.
right, yes. So, can you please explain, like, intuitively this GM into Z out model for this particular case? Like,
So it's
I mean, it
GM
was,
and Z out. GM into Z out comes from our basic CS amplifier, right? So the gain of
yes.
CS amplifier. And here also it is more or less a CS amplifier only. So if I say that I give my input here, so this is gate and I'm taking my output from drain. So it's again CS only. It's just modified because of the another transistor coming into picture. Otherwise, it was also a CS amplifier, right? Here as well.
Uh, yes, so
So
I got the Z out part, like Z out is
yeah.
fine, but the GM part is, I'm like, it's confusing because of like
Okay, okay. So the
transistors.
GM, yeah, yeah. So the GM in the formula comes from this input transistor. So this GM comes from input transistor.
Okay.
So this GM is of input transistor. Like if there are two transistors and you have to find the GM, so GM always comes from your input transistor. Wherever you are giving input to, from there only your GM will appear. Because if you draw the small signal model, then also you will understand like how things changes. So if you simply draw this stacked transistors, the small signal model. No? From there, you can clearly see that the GM which is influential is actually the GM of the input transistor only. So this GM will
Okay.
be input transistor and Z out will be at the output node.
Right.
Yeah.
So for the small signal model, let's say, so the gate of the three transistors which are on the like top of the input transistor, will they
Right.
be like short, grounded, like virtual
So see,
grounded, or?
when you have these type of circuits, no, we call them mirror circuits. So what we mean by that is if we solve one part of the circuit, the other part will be exactly same. So what we do is we only solve half of the circuit, like one part of the circuit, because after this I'll be moving into like in next lecture we will be discussing differential amplifiers, which are again these two type of like by two sides. So they will have two branches and connected. So I'll talk about them. So there also we don't consider the whole circuit, rather we only consider one branch of it because we say that this is a mirroring circuit. So if we solve one branch, then the other branch is just the same. So that's why here, if you want to solve this properly, so you can only consider this half where there is no mirroring, no, like there is no gate to drain shorting. That particular this side output side you can consider, and from here, so you can only consider this particular, uh, okay, so you can only consider this particular part of the transistor, this particular half, you can solve the small signal model by using this half only.
Yes, so I was just like wondering whether the gate of this transistors for the
Hmm.
small signal model would be grounded. I mean, pairing the bottom one, the input one, for
Okay,
other
yeah,
three.
so other three, right? So,
Yes.
yeah, so here you are giving the input, right? So we consider this to be our AC point. So this is our AC point. We will keep this intact. So this is my AC point 1. Then here I will have my AC point. Here I will have my AC point, here I will have my AC point. Other than that, gates, what I'll do is I'll consider them AC grounded. Just for
Um,
simplicity, I'll
okay.
consider these to be my AC grounded system. So here also this is grounded, this is grounded. Only I'll have these 4 points where my AC will appear. So this is more like let's say you are giving input as at this point. So what are the voltages which will be basically like what are the points which will be affected because of this particular AC input? That is the basic idea. So it is clearly evident that the gate voltage will never be affected, right? Because gate is completely a separate terminal. There is no connection between gate and this point. Source voltage will be affected, but gate will never be affected. So that's why we
Um,
can consider those gates at AC ground.
yes, I was like considering the same thing, but
Yeah.
then there occurred another thought. Let's say,
Okay.
I mean, if I look at the left side of the circuit, left half, so the
Yeah,
gate
Rafa.
and drain, yeah, gate and drain are connected. So
Yes.
like, so that would in every transistor, gate and drain
Yeah,
are
yeah.
connected. So
So
like
that's
that
why,
created a
so
confusion.
yeah, yeah. So that is the reason why we consider the right side transistors. Because as I mentioned earlier also, when gate and drain, so gate and drain connected means basically your input and output ports are shorted, at least in case of our CS configuration, right? So the
Yes.
moment when you start connecting input and output ports, no, it is very difficult to analyze the situation. That's why the Miller theorem was also found. It was found because how to deal with the elements which are connected with, between both input and output port. It's very critical to, and it's very like it's very critical and it's very difficult to understand that behavior. So that's why Miller came up with the problem. So that is the reason we don't go for this mirroring side to solve it because we know that it is complicated. And we also know that the opposite side, if I find the behavior, and since the circuits are just mirror image of one another, so the response is mirror image, so I can apply the same behavior to the other side. So that is the reason we go by solving the right hand side half of the circuit.
Okay, got it. Yeah, that clears the
Got it?
confusion. Yep,
Yeah.
thank you.
Yeah. Okay, any other doubts? Any confusion? Okay, so if no confusions, maybe we can move to the next problem. So again, this is question. So in this particular circuit, see here again we have these mirror circuits. So this is again basically a mirror circuit, or we can say current multiplier circuit. Now it will depend on the factor of W and P. So here you can clearly see that WP is here it is WP, here it is 21 times WP, and here Wn is Wn. So you can get from the factors that it is somehow like increasing your current or multiplying or your current, right? So we call these circuits as current multipliers. Okay. So here, let's quickly dive into the problem. So we have Vt is zero point 0.3 volts and Cox by 2 is 80 microsieverts per volt. Maybe Cox by 2, 40 microsieverts per volt. Power supply, this is 2.5 volts. Wn is given to be 10 microns. Microns is micrometers, okay? 1 micron is 1 micrometer. And Wp is 20 micrometers. So all the devices have a length of 1. So L is 1 micrometers. And R, this R is 8. This R is 8.6 kilo ohms. And okay, with this, we have to find the value of I, right? So now see, first of all, your W in WP are Everything is given, right? So from there we can find the current here. So let's first number the transistors. One, 2, 3, 4, 5, and 6. We have total 6 transistors. So we know that I1 equal to I2, considering that these two are in series. So that means UP by 2, WP by L, VSG minus VT whole square VTH is mu n Cox Wn by L, VGS minus VT of whole square. Right. So from here, VT of all the transistors is 0.3, so VT will be there. Other than that, let's substitute. So 40 into WT is 20 by 1. VSG minus 0.3 square equal to 80 into 10 by 1. VGS minus 0.3 whole square. So from here, it is clearly evident that VSG1 is equal to VGS2. So this is clear to us that VSG1 equal to VGS2. Now if I write my current, like this particular current KVL from VDD to ground, so it is again 2.5 equal to VSD1 plus I into R plus VSD2, or it can be written as VSD is equal to VGS, VGS equal to VDS, since there is a mirroring effect. Basically, the gate and drain are shorted. So because of that, we have VGS 2 times of VGS1 plus I into R. So 2.5 equal to 2 into VGS1 plus I into R, so it is 800 micro, 800 micro into VGS minus 0.3 whole square. So from here, we know that S is grounded. So from here, we can find the value of VGS. This is one thing that we can find. But yeah, anyways, so here we found out that it will have some current I1, right? So here, if it has the current I1, now that same voltages are connected to, so here it is Wn, so transistor I2 and I4 are like matched transistors. So from here, if we see, I2 will be equal to I4 since these two are matched. So if I2 equal to I4, so to solve this, simply see I1 equal to I2 because these two are in series. I2 equal to I4. Why these two are equal? Because they are matched. Matched transistors like VGS is same, your W is same, L is same, everything is same. So I4 will be equal to I2. Now we know again I4 equal to I3. This is because of series. So if I4 equal to I3, that means, but here like WP, and it is 21 times of WP. So that means your I4 transistor, so I1 was mu p Cox WP by 2L VSG1 minus VT whole square. I4 is mu p Cox WP into 21 by 2L VSG4 minus VT whole square. But VSG4 equal to VSG1. So here if we see I4 is 21 times of I1, correct? So I4 is 21 times of I1. Okay, now coming to this transistor here, if we see this, oh, this was I3, sorry, this is I3. I'm talking about I3. And I4 and I2 are equal. So this is I3, this is I4, and this is, let's say, I5. So by applying KCL, we will find that I3 equal to I4 plus I5. So we know I3, it is 21 times of I1 equal to I4 is I1 plus I5. So I5 is 20 times of I1, right? So this is 20 times of I1. And here again, I5, like transistor 5 and transistor 6 are matched because their gate voltages are same. Source is connected to ground. So VGS remains same. They both have WN. So that means I5 equal to I6 equal to 20 times of I1, right? So just here we need to find the value of I1. If we find the value of I1, we can simply multiply it by 20 and we'll get this I6 or the I which is asked in the problem. So as I mentioned here, the moment we find the VGS from this equation, we will get our I. So the final I, that is I6, turns out to be 2.558 milliamperes. So this is the value of our current through this final transistor I6. Is this clear to everyone? Any doubts how we solve this problem? Yes. So check, first of all, what you check, check for VGS. If a transistor has same VGS, it has same W by L ratio and same mu and Cox, like all the constants are same and VGS is same, that means same current will flow through the transistor. Okay. Any doubts? If you have any doubts, please unmute yourself and ask. Any doubts? Let me know it as X. KCL at X. Yes. No doubts, right? Okay, so maybe we can move to the next problem. So this was question, which question? Question number 6, right? Sorry, question number 3. Question number 4. Yeah, so meanwhile, I'll just be back in a minute. Why don't you people solve this problem? Now, see here you have A, B, C, D, which are the multiples with the uh, transistor widths, and you have to find the current I copy. Okay, I'll be back in a minute. Meanwhile, please solve this problem. Hello. Okay, the screen turned off. When did this screen go off?
It's nearly 30 seconds ago.
Oh, so you people could not see the problem or what? Okay, anyways, you can see the problem now, right?
Yes.
See, so basically, getting the value is not important. It's just let's talk about the factors, right? If we get the factors right, then we will be like, we'll be able to solve it. It's just multiplication. So it is given that A is 1, B is 4, C is 3, D is 1. Okay. See, here it is I ref. So A is 1, that means IREF is flowing through this. Now, when you see the transistors A and B, they have same gate voltage and same source voltage. That means VGS is same. VDH is same for all the transistors. So by using that convention, if you see your IB is 4 times of IA, right? Because the width has been increased by 4 times. Correct? the width has been increased by 4 times. Now, you know IB should be equal to IC. So that means IB is equal to IC. Now, from the factors, it's if you observe very carefully, ID should be IC by 3, correct? So here ID should be IC by 3. That means if 3 times, so it's like 3WP equal to WP. So this is for C, this is for V, but they have to be equal. So from there we get like this to be ID equal to IC by 3. And now if we substitute it here, so it will become ID will become 4IA by 3. Correct? So any doubts in this? How we got this? See, first we started with IREF. Okay? Whatever is the current and whatever is the factor that is equal to IREF. Now it says it is equal to 4 times width and VG is same for both the transistors. So when VG is same, so if we talk from, I'm calling it KW by L, okay? KW by L VGS minus VT whole square. I'll be writing in this format. So first of all, K, uh, K is constant for N transistors and K is same for the P transistors. Now this is W1 L1 equal to K and WB by LB VGS minus VT whole square. Now here we know these two are equal. K is equal, L is equal. So W equal to, oh sorry, this cannot be equal. This will be VGS is right exactly. Here this is not equal. Series में only it will be equal, right? यहाँ पे they are only connected. So here what we know is VGS A equal to VGS B. Now KWA by L VGS A minus VT whole square equal to IREF, right? So KWB by L VGS B minus VT whole square. So if I substitute it, it will be K into 4 times of WA by L VGS B equal to VGS A minus VT whole square. So this becomes 4 times of IREF. Correct? Now this is IB. This is IB. Okay. Now IB should be equal to IC. This is because of series. Right? So K into 4WA by L VGSA minus VT whole square is equal to K 3 W2 by L VGSC minus VT whole square. So this comes from the series. So this is like basically IB equal to IC. So this is 4 times of IREF equal to 3 into Kw2 by L, V is G, is C minus Vt whole square. Now here V is Gc equal to V is Gt, correct? So it is 4K W2 by L, V is Gt minus Vt whole square. So no, D is 1. Okay, D is 1. So इसको simply यहाँ से करिए 1 times Kw2 by L, V is Gd minus Vt whole square. This is Id. So here if we try to substitute it, we get Id to be 4 by 3 Iref. Is this clear to everyone?
Yes.
Yeah. So in this problem, it's very easy to handle this kind of mirror and current multiplier problems. Simply you have to keep in mind the factors and where you have to. So earlier here we used a KCL, right? So here the KCL was used because the this particular current was going into the drain of another transistor. But if, let's say, this branch would have connected to the gate of another transistor, we need not to use KCL because we know that gate current is zero. So just small things, very basics you have to keep in mind to solve this type of problems. And by this method, you can solve up till, like, let's say if there are 20 transistors also, you can simply solve this kind of problems. It's just you have to keep in mind the factors, okay? So what are the factors? Width factors like width multipliers, and you simply start equating them, and then you can solve this problem. Any doubt in this kind of problems? Anyone? Hope there are no doubts. So is there any message? Okay. Right. So let's move on to the next problem. See, again, we have similar kind of problem. So here, okay, so why don't you people solve this problem? Okay, I'll write down the factors. It is 8, this one is 7, this is 8, this is 1, and this is 6. Okay, you need not to give me the value, just tell me the factor. Like I copy is x times of I ref. I want to know what is x. Just tell me that.
Uh, so it's 6 into 7 by 8.
6 into
Oh, yeah, 6 into 7 by 8.
6 into 7 by 8. Okay. What about others? Yes, what about others? Hello. So do you want me to solve this problem or will you be able to solve it on your own?
We'll try.
Uh,
Okay,
I
why
think
don't
that
you
is 1.
people?
Sorry, I think that is 1 minus 6 into 7, something like that.
So try solving this. It will not take you more than 5 minutes. I don't want the values. I just want the factor. Maybe you take 5 minutes. After that, I'll solve it. But take 5 minutes and try to solve this problem.
So it is 34 by 8 I copy.
Okay, so I got one answer is it's equal to 34 by 8. Okay, this is option A. What about others? Yes, any other factors? Any other options? Anyone?
Ma'am, can you explain the C part?
C part, sorry, I didn't get your point.
Ma'am, how will we compute the IC part? OI.
Oh, okay, okay. So how will we see IC part? No, so C. First of all, you can see that C is the N-type transistor, correct?
Yes.
So the C, like the same point is connected to A, B, and C. So all three transistors have same VGS. So that means your IA and IC will be equal, right?
Yes.
Because VGS is same and the factors are same. So from there. So how many of you have solved this problem? Can you please raise your hand? And what are the solutions that you people got? What are the answers? I got one option is 34 by 8. What about others? What are your answers?
25 or 21.
Okay, option B is 25 by 21.
Yes.
Okay. What about others? Yes, the people who are raising their hands, what are the factors you people getting? What is their hands? Okay, so we have got two options, right? And one of them is correct. So maybe let's quickly solve this problem, okay? See, IA is IREF. IB is 7 by 8. So it's like it's easier understanding. Maybe I should not use short bits. I equal to IREF. It will be K AW1 by L VGS minus VTH whole square. So this is K 8 W1 by L VGS minus VT whole square. Now if we talk about IB, this is IREF. IB, it is KB W1 by L VGS minus VT whole square considering same VG. So IB will be 7 KW by L W1 by L VGS minus VT whole square. So that means 7 and this particular part. So which is basically IREF by 8. So IB you got it as oh, IB you got as 7 by 8 IREF. Now if we see IC, so IC is equal to IA equal to IREF. Why? Because the factor of 8 as well as your VGS is same. So IC is equal to IA equal to IREF. Now IB should be equal to IB because of series, the same. So that means 7 by 8 IREF is equal to factors 1. So KW2 by L VSG minus VB whole square. So this is equal to ID. Once you got ID, okay, once we got ID, we know that from here VSGD equal to VSGE because same gate voltage source are connected. So this. So IE is K into 6 W2 by L B is GP minus VT whole square. So IE is 6 into K W2 by L B is GE minus VT whole square, which is 6 into IB is IE. So IE is 6 into 7 by 8 IREF. This is IE. Okay. So now if I apply KCL at X. So by applying KCL at X, I see that IE equal to I copy plus IC. So which is 6 into 7 by 8 IREF equal to I copy plus IREF. So I copy becomes 6 into 7 by 8 minus 1. This is basically 42 minus 8 by 8 IREF. So I copy is 34 by 8 IREF. Is this clear to everyone how we solve this problem? So the final factor is 35 by 8. So somebody said 25 by 21. This is wrong. So can you find where you were going wrong? Like, could you find your mistake?
Yes.
Yeah. Okay. So just be a little careful, and if you feel like you are not very confident in directly answering the problem, go step by step. As I solved step by step, no, it will take 2 minutes your time, 2 minutes of your time, but you won't land up getting a wrong answer. And these problems are very easy. You just have to keep the factors in mind and just have to start equating the currents. Okay. So is this clear to everyone? Still, anybody has any doubt in this kind of problems? Anyone? If you have any doubt, please unmute yourself and ask. No doubts, right? Okay, so if you don't have any doubts, let's move on to the next problem. So here in this problem, you have to evaluate the transconductance. Transconductance is Gn. So here it is already given. It is I out by Vn of the transistor. Assume the op-amp is ideal. Assume the op-amp is ideal and R is 16.1 kilo ohms. So give your answers in microsiemens. Okay. So first of all, what do we mean by op-amp being ideal? So this is your op-amp. Okay. When we say our op-amp is ideal, that means we consider VA equal to VB. This is the first assumption. And then we have, so it is like gain is infinity. So it comes from the same thing. Zn is infinite. Z out. Z out we don't talk about generally. So Zn is infinite. So these are the major things that you know from your ideal outcome. So by this, we know that this terminal, like there won't be any current going into the op-amp. Since Zn is infinity, so this particular current is zero. So if that current is zero, whatever is current flowing through this particular transistor, so this particular transistor, what is the current? So this is I. I is V in by R, right? So I is V in by R. Now this current is flowing through this transistor which is given. Since both the transistors have same bias, so your gate voltage is same, source is connected to the same same terminal, so that means VGS is same. Considering that the transistors are matched, so VT is same. So that means whatever is current flowing through the transistor A, the same current will flow through the transistor B. So that means I out should be equal to I. So I out would be V in by R. So I out by V in is 1 by R. So this is what was asked. So any doubts in this particular problem? Any doubts in this problem? Did you understand how we solved this? So first of all, ideal op-amp we use the condition that there won't be any current going inside the op-amp. So that's why we didn't have to use any KCL at this input point of the op-amp. We simply use the current. After that, you can see that they are like mirror circuits only, since their VG and VS are connected together, so making them matched. Okay, how I out equal to I? Okay, so for I out equal to I, see, in this particular circuit, it is given that it is an ideal op-amp, so I equal to 0. You understand this? I equal to 0. So this comes from the property of op-amp. So I is 0, because of which the current which was flowing through the resistor R will pass on this path. Now so this basically encounters your transistor A. So the current through the transistor A is I. Okay. Now you see here also the voltage is V bias. Here it is V out. So both the points are at V out. That means VGS A equal to VGS B. There is no information given about the transistors, so we consider that transistors are matched. So that means WA equal to WB, LA equal to LB. Now, if you write the current equation, how it will look like: VGS A minus VT whole square for transistor 1, like IA. For transistor 2, it will be KWB by LB, VGS-B minus VT whole square. Now we know that the current through the transistor 1 is I, and the current through the transistor 2 is I out. So we also know that all these factors are equal, so which ultimately make your I equal to I out. Is this clear? Is this clear? Okay. So any other doubts? Did you understand the problems today?
Yes.
Okay. So if you don't have any doubts, so I prepared only these many questions for today's session. So maybe we can break over here and meet next week. Or if you have any
Kindly
doubts,
share
we
this
can discuss.
video.
Sorry.
Kindly share this video.
This yeah, video, all the videos are uploaded on YouTube. So
Okay, ma'am. Thank you.
yeah, after every session, the videos will be uploaded to YouTube. And also you will receive this PDF. So all of you have this Google Sheet, right? Where you can find the link to the folder for this PDF. Anyways, if
Yes.
so just in case if you don't have access to the like to that sheet, maybe you can subscribe to my channel. So the moment I upload it, you will get the notification. And also, I'll make sure that I mention the link for this folder where you'll find all these PDFs, solved PDFs, whichever the document that I'm using. That link will also be there, so you can simply upload, like you can simply view that PDF over there. Okay, so it will be in the description of the video. Okay. So yeah, if there are no doubts, maybe we can break over here and meet next week. That's all for today. Thank you, everyone.
Thank you, ma'am.
Okay, ma'am.
Thank you.
Thank you.